today then we're going to talk about photochemical reactions. And these were very important at the origin of life because in fact the UVC light, which was arriving at Earth's surface at the beginning of the Archean when there was no oxygen, so therefore no ozone. So this UVC light could have arrived at the surface of Earth. This light seems to be very important for producing the fundamental molecules of life, like the nucleic acids, the amino acids, the fatty acids, which form the vesicles or the walls of the cells, and even some pigments. And again, the pigments were probably there not for some kind of photosynthesis with UVC light, but rather for dissipating, producing entropy again. So it turns out with this UVC light from about 210 to about 285 nanometers, and water and molecules like hydrogen cyanide and carbon dioxide is basically sufficient to produce most all of the nucleic acids and most of the amino acids. For some of the amino acids which have sulfur, we might have needed also hydrogen sulfide, which is one of the gases which comes out of volcanoes. But for the basic amino acids, this is all you really need: hydrogen cyanide, carbon dioxide, and water. So these two molecules dissolved in water under UVC light. So we're going to talk about the photochemical reactions which gave rise to these fundamental molecules, and some of the details which are important to understand how the structuring of these molecules would occur naturally in nature, only assuming that nature tends to optimize the dissipation of photons. Okay, so we have chemical reactions, photochemical reactions, which are occurring, which produce these nucleic acids, for instance, these bases of DNA or RNA. And we also have other photochemical reactions, for example, this dissipation, which is the absorption and dissipation. So that is through a conical intersection, and this is called internal conversion. So we're converting the electronic excitation energy of the base, the nucleobase. We're converting that excitation energy into heat, which is then dissipated into the water. So first in the vibrational motion or the vibrational states of the molecule, which could be adenine, for example, and then into the vibrational states of the water. So one incident photon in the UVC could be converted into about 30 or 40 infrared photons, and that is entropy production. So this is also a photochemical reaction known as internal conversion, and there are others also like fluorescence, phosphorescence, and as I mentioned, the production of these fundamental molecules. So these are production of molecules of photochemical reactions for the production of these molecules. So before getting into the details of these photochemical reactions, let me just briefly describe what in fact light is. So classically speaking, we can look at light as a wave, which has a certain wavelength. Okay, we're going now in the diagram on the upper left, and a certain intensity, which corresponds to the peaks. And for electromagnetic wave, we have both an electric field and a magnetic field at right angles to each other. And so we have this vibration in a particular plane. Now, if this plane is the same for all of the light, then we call it plane polarized light. So for example, in this diagram, we have vibration only in one plane, then we call that plain polarized light. But normally light is unpolarized. For example, light coming from the sun is essentially unpolarized. So that means that we have this vibration occurring in different planes at different angles. And so we have rather an average, which turns out to give us the whole unpolarized light. Now, light can also be circularly polarized. For example, if we have a single scattering of unpolarized light, that gives rise to linearly polarized light. And if we have internal reflection at a surface, for example, the surface of the ocean with the air, then we can get circularly polarized light. And in circularly polarized light, the angle of the vibration is constantly changing. Okay. So it's this diagram in the center, in the upper center. And it depends on whether it's going in the left direction or in the right direction. There are two possible directions, and these correspond to different angular momentum in units of Planck's constant h. So we can have two circularly polarized states, right and left. And this, as I mentioned, is very important for the origin of life, because we know that many of the fundamental molecules of life have their right and left-handed versions, which in fact have the same Gibbs free energy, which means that they are equally prevalent at a given temperature in an equilibrium situation. And this circularly polarized light can select one over the other. And maybe we'll talk more about that in another class when I talk about the homochirality of life. But for now, just take into consideration that at the ocean surface, we have the largest amount of circularly polarized light on the surface of Earth. And in the morning, at a given position, at a given viewpoint, it is going to be different than in the afternoon. It's going to be, for example, left in the morning and right in the afternoon. So this light comes from a continuous spectrum from very short wavelengths, which are known as cosmic rays or gamma rays. In fact, the wavelengths could go as short as the Planck length, which is the smallest length because of quantum mechanics allowed for space, which is about 10 to the minus 35, if I'm not mistaken, meters. And it can go all the way up to infinity, but probably not infinity, because we know, or we assume, or we suppose that the universe is closed and it has some kind of a finite volume. So we have this very wide range of wavelengths, all the way from almost infinity to the Planck length. And the visible light is only a very small portion of this, which we are sensitive to as humans. We can see from about 380 nanometers all the way up to about 720 nanometers, this visible range. And then we get into the ultraviolet at shorter wavelengths. And apparently this is where life started with this light, because only this light has sufficient energy in each photon to be able to make and break carbon double covalent bonds. And most of the fundamental molecules of life are double carbon covalent bonds. They have these conjugations, double bond conjugation. So what I want to emphasize is that this is the visible spectrum, but life started probably using only ultraviolet light. Because with visible light, there's not enough energy to make and break or reform carbon covalent bonds. There are for single carbon covalent bonds, but not for double bond molecular structures. And as we have seen before, this is the calculated solar spectrum at Earth's surface. At the origin of life is the black line. So we have this UVC peak at the far left, and we have this other peak in the visible, and then it goes into the infrared. And again, these lines here, which are vertical, they correspond to the absorption of water in the atmosphere, Earth's atmosphere. And there's also a hydrogen ion absorption in the atmosphere of the sun, and that's why they get this little dip here. And at the origin of life, we assume that we have a particular set of gases, which were the same gases which were coming out of volcanoes. And with ultraviolet light on these gases, we can form these aldehydes. And that's been done experimentally. And we know, for example, this is formaldehyde, and it absorbs in this region. So that's why there's a little gap here in this region. And hydrogen sulfide, which also comes out of the volcanoes, absorbs lower than about 210 nanometers. And the carbon dioxide absorbs at even the shorter wavelengths. So this little peak amplified looks like this. And this little peak of UVC light was arriving at Earth's surface for about 1,000 million years, which is a very long time. So we can imagine that life would have at least adapted to this ultraviolet, this UVC light. Many people believe that life could never have adapted to this light. And so that's why it's more likely that life started at the bottom of the oceans where there was no light at all. But we believe that this UVC light was very important, particularly for these photochemical reactions, which I'm going to talk about today. So now if we plot the maximum absorption of the fundamental molecules, that is these molecules which are in the three domains of life. So we have the archaea, the bacteria, and the eukaryote. If we plot their maximum absorption, some of them have two peaks of maximum absorption, so we plot the two peaks. So some of them appear twice because of their two-peak absorption. But most of them fit very nicely around this spectrum which was arriving at the Earth's surface at that time. And we see a gap in where we don't find any fundamental molecules absorbing at all in this UVB range. And then they start absorbing again in the UVA range, where there again was light at the beginning of the arcane. So this is including nucleic acids, amino acids, fatty acids, which make up the vesicles or the walls of the cell, sugars, ribose, and glucose, vitamins, vitamin A, vitamin D, and correctly vitamin E is here, coenzymes and cofactors. These are like the catalysts for the biochemical reactions which are occurring in life in the three domains. So this is an example of the absorption spectrum of DNA. So we're absorbing again very strongly. It in fact increases here, and all the way from about 200 or 210 nanometers, going up to about 300. When we get to even shorter wavelengths, it's still absorbing. But now what's happening is that it's ionizing the molecule. So it's removing electrons from the molecule. And the more electrons that you remove, the more unstable is going to be the molecule until it finally breaks apart. So that's probably why we're not finding these organic molecules on the surface of Mars, because Mars has no ozone to protect it from this very short wavelength light. So if it did have an atmosphere with oxygen many thousand millions of years ago, and it was producing these organic molecules, probably, I don't know why it's jumping on its own, probably those molecules would have been destroyed by this ultraviolet light below 210 nanometers or 200 nanometers. And what else I want to show here is that we have an effect which is known as the hypochromic effect. That is, when DNA is in double strand, it absorbs less light than when it is in single strand. So the difference is about 25 to 30% difference, 20 to 25, depending on the length of DNA and on the sequence also. So this is called the hypochromic effect that we see here. From single strand to double strand, we start absorbing more in the single strand than in double strand. So this is an interesting spectrum. Now it has a width. We're going to talk about the width, how the width comes about. And it has an extinction or an absorption coefficient, call it the molar absorption coefficient, which determines how well it's absorbing the light and dissipating that light, because to absorb another photon, it has to dissipate the excited electronic state. So to get an excitation, so this is then between the ground state here and the first excited state, electronic excited state. Remember, we have vibrational states superimposed on the ground state here. So there are different vibrational states, and these are also quantized. But to get to the first electronic excited state for DNA, we need a certain frequency or wavelength, so, or a certain energy. So this corresponds at, for example, the DNA is absorbing maximally at about 260 nanometers. That corresponds to about an energy of 4.77 electron volts. So we need that energy to be able to excite the state. But there is a width, so we don't have to be exactly, we could be a little bit less or a little bit more, and we would still absorb it. So that's called the width of the transition, or delta E. So, and that corresponds here to this absorption spectrum. It corresponds to the width, for example, at half maximum. That is delta E. And that width, of course, is determined by the lifetime of the state, of the excited state. So, and that's determined by the Heisenberg uncertainty relation. No, delta E, delta T has to be greater than or equal to h bar. This is the Planck constant over 2 pi. So therefore, if delta T is very short, very small, then delta E has to be great. The width of the transition is greater. So for dissipation, if we're talking about entropy production due to dissipation of photons, the greater the width, the better we are, because we're absorbing over more of the spectrum. And if we look at this spectrum for DNA, we're actually absorbing very well this range from about 205 to 285 nanometers. We look at this again. Oh, sorry, the spectrum. Better to see it on this one. Huh? We're absorbing very well over this range. So that width is determined by the lifetime of the excited state. And the factors affecting the lifetime of the excited state can be a number of different physical phenomena. For example, collisions with neighboring molecules can lead to the excitation. This, of course, would increase with the pressure, because with increased pressure, we have more collisions. So we would have a shorter lifetime, delta T. We also have the Doppler effect. So the lifetime also decreases with temperature. So in fact, the Doppler effect, because of the movement of the molecules, this delta E here will be greater because there exists this Doppler effect. So a greater delta E means a shorter lifetime delta T. Now, the most important for these fundamental molecules is what is known as vibronic or non-adiabatic coupling. And when they say non-adiabatic coupling, they're talking about the coupling of the potential energy surface, the vibrational states on the electronic ground state, so these vibrational states here, with the vibrational states on the first electronic excited state. So we have a potential energy surface on the first electronic excited state, and we have the vibrational states superimposed on that electronic excited state, and we have vibrational states superimposed on the electronic ground state. And there can be a coupling, and that is through what is known as the conical intersection. And that causes internal conversion. So very rapidly we get dissipation from the electronic excited state to the ground state. So that decreases the lifetime, which means delta E increases. And that's basically why we have this large delta E for these fundamental molecules, because the lifetime is so short. The lifetime for these molecules is on the order of picoseconds, or even less than picoseconds, 1 picosecond for some of these fundamental molecules. So this is due to the conical intersection, which I'll describe in a future slide. So what are the possible excitations and de-excitations for molecules? So this is known as the Jablonski diagram. So here S0 refers to the electronic ground state, okay, and it's a singlet state. That means spins of the electrons are in opposite, so we have no spin, net spin equal to 0. And we have, this is the first electronic excited state, also with spin 0, okay. Spins are anti-parallel. So these are singlet states. That's why they are written with S. S signifies a singlet state. So we can have a photon causing an absorption to the first singlet excited state. And then we can have internal conversion, which is this on the left. So the first excited state goes to the ground state through vibrational dissipation. So that is what the fundamental molecules are all about dissipating photons. They do that very rapidly, and that is in picoseconds. But also we could have a larger lifetime and giving rise to fluorescence, where we emit another photon from the first singlet excited state. That's called fluorescence. We can also have intersystem crossing, which takes us from a singlet state to a triplet state. That's the state in which the spins are aligned, okay, of the electrons. And in this state has a much larger lifetime, because it's a forbidden state, that it can only happen through interaction with, for example, an oxygen molecule, which could be in the water, the system. For example, if we're talking about fundamental molecules in water, if we have an oxygen in the triplet state, which is rare, but it can occur even at normal temperatures, then we can get a coupling, allowing the system to go from a singlet to triplet state. So we allow the molecule that interacts with this oxygen molecule in the triplet state. So we can have a conservation of angular momentum for the spins and go from a singlet to a triplet state. And as I mentioned, these triplet states are longer lived because they are forbidden because of conservation of spin or spin angular momentum. So this is known as intersystem crossing. And well, we can also have, when we get to one of these vibrational states on the first excited triplet state, it can go down to vibrational dissipation. Then it can go to phosphorescence, or it can also go through another type of internal conversion to the ground state. But these are longer lived states. So for example, this internal conversion is on the order of picoseconds, 10 to the minus 12 seconds. Fluorescence is on the order of nanoseconds, 10 to the minus 9 seconds. And phosphorescence can be even as large as seconds or hours, you may have known some of the toys for children which fluoresce when you expose them to light and then you put them in the dark. They can fluoresce for various hours. And that's because the light that they were exposed to allowed them to go to this triplet state, and they're trapped in this triplet state. And so to go to the ground state, they only have this phosphorescence decay channel, which is the emission of light, but delayed. So up to seconds or even hours for some substances, some molecules. Now, what does the absorption spectrum look like and the fluorescence spectrum? So here we're just considering the absorption and fluorescence spectra. So for example, this is the ground state, okay, and a photon is absorbed and it goes to the vibrational, this is the first vibrational excited state of the electronic excited state. So this corresponds to the electronic excited state, and that is the electrons around the molecule. Remember that in a molecule, the electrons don't belong to a particular atom. They can be shared, especially when there's covalent bonding. So we have a sharing of the electrons. So it is like a collective excited state of the electrons. And this is the potential energy surface, and these are the vibrational states superimposed on that potential energy surface. So here we're going from the zero vibrational state, the ground state, to first vibrational state of the electronic excited state. And that gives rise to this absorption peak here. Okay. We can also go from zero to the second vibrational excited state here. This is this state here. And this is 0, 2. Okay, this is number 2 the vibrational state. This is number 1. This is number 0, 1, 2, 3, and so on. So if you go from here to here, it's even larger energy. So you go to shorter wavelength. This is a function of wavelength, increasing wavelength towards the right. So decreasing towards the left. So this absorption corresponds to this peak. So these peaks that we see in the absorption spectrum are basically vibrational states superimposed on the electronic excited state. Now for fluorescence, it's just essentially the reverse. It's like the flip of this. So for example, from the first vibrational excited state on the electronic excited state to the ground state here would be this 0, 0. So going from 0 to 0. Remember, this is 0, 1, 2, 3, so on. So that is this peak. For the fluorescence peak, it's when we emit a photon and go back to the ground state potential energy surface. And 0, 1 would correspond to this line here. Okay. This is 0, 0 is this line. This is 0, 1, and 0, 2 would correspond to this one, and 0, 3 would be this one. Okay, so that's the absorption spectrum and the fluorescence spectrum. Now we also have something, because we have quantum systems at this scale, we have to treat the system quantically. So we have what are known as quantum selection rules. So the first one is the spin selection rule, that the excitation to the triplet state is spin forbidden, as I mentioned, because we're not observing angular momentum. But it can occur due to the interaction with a paramagnetic solvent molecule, for example, oxygen, as I mentioned, in its spin triplet ground state. So again, this is referring to this possible going through intersystem crossing here by the molecule interacting with this molecule, which is the oxygen molecule in its triplet state, can go to the triplet state. So it's basically forbidden, but it is allowed because of interaction with other molecules in the system. And it can also be interaction with the spin orbital momentum, angular momentum coupling, which I won't get into, but that's due to the electrons around, the inner electrons around the nuclei. So for organic molecules, under normal laboratory conditions, the singlet state for excitation is favored over the triplet state by about 1,000 to 1. So it's much more frequent that we're going to get excitation to the singlet state. But sometimes excitation to the triplet state does occur. And that allows us to have different set of photochemical reactions as excitation to the singlet state.
Professor.
See, Claudette. Yes.
Okay. How the I don't know if a triplet state occurs, how this affects the photochemical dissipative structures, like how it affects the photochemical reactions. What is the like? ¿Qué tiene que ver the first and the first quantum selection rules with our theory?
Okay, I'm going to get into that a little bit later. So if you just hold on a minute,
Okay,
we're talking about the different possible types of reactions which can occur in different states in the triplet and singlet state. Okay, but if I don't properly answer your question in the following slides, you ask me again at the end. Okay? So let me just go through these selection rules first. So that was the spin selection rule. And number 2 is the angular momentum selection rule. So electronic excitations are affected by electronic dipole transition, which is mu. Usually we use the symbol mu for the dipole transition. And this transition is allowed if the transition momentum integral, okay, so this is now we're going to quantum mechanics. Some of you in biology will not understand any of this, and don't worry about it, but for those in physics, you know that this is the imaginary conjugate, the wave function, and this is the electronic dipole transition, and this is the second state, so going from state 1 to state 2. So it can be from the ground state to the excited state. And if we do this integral over minus infinity to infinity, then if this integrand here is odd function, that is, if f at x, if we define this phi star 1 mu times phi 2 as being f, then if we put f at x and f at minus x and they're not equal, then we have an odd function. So if we're going to integrate from minus infinity to infinity, it's going to cancel out. And we're going to have 0. So then there would be no transition. Okay, so we need to have the whole thing has to be symmetric if we're going to have a transition. So therefore, since mu is an odd function, because it's the dipole transition, so it depends only on the distance, not on the square of the distance between the two charges, no positive and minus charge, that gives us a dipole, which depends on the separation of the two charges, which depends on x or the coordinate. And so it's an odd function of the coordinates. So that means that in order to have this integrand being symmetric, that we need different symmetries for phi 1 and phi 2. That is, for the molecule in initial and final states, they have to have different symmetries. So for example, we can have even going to odd. And that gives rise to then to this electronic angular momentum selection rule of delta L. This is L, the angular momentum quantum number, has to be plus or minus 1 in order to have this being symmetric, in order so this integral doesn't go to 0. So for example, in the case of atomic systems, okay, so we have just atoms here. This transition from 1s to 2s is forbidden. So this cannot be a 1s and a 2s state here. This will be forbidden because this will give us a non-symmetric integrand. And so doing the integral is going to give us 0. But we can have, for example, a 1s to a 2p. And for the case of molecules, well, the angular momentum number, okay, L equal to 1 is defined as a sigma. So we cannot have, for example, sigma L1 going to, sigma is L equal to 0 going to delta, which is L equal to 2. This transition is forbidden because we're going to again have a asymmetric integrand. But we can have, for example, sigma going to pi. That is allowed. So pi is 1 and sigma is 0 in angular momentum for the molecule, which corresponds to the angular momentum of the electrons in their orbitals around the molecule. Okay, so we have these two quantum selection rules, spin selection and angular momentum selection rule. Basically saying that we have to conserve angular momentum, whether it's spin or it's orbital angular momentum.
Professor,
Yes?
can you return to the last slide?